Hello everyone. Today we are going to explore modeling a paper-making process with the Wolfram Belt Dynamics library. My name is Vedat Şenol and I will be your presenter for this session. As you already know, from fitness equipment to automotive systems, roll-to-roll systems are everywhere for efficient power transmission and precise control. These systems can be found in various applications as you can see here, from treadmills used for fitness to the serpentine belt in car engines and even in complex paper-making machinery. Uh, Before we dive into today's topic, let me introduce myself briefly. I work as an applications engineer at Wolfram in Sweden. I hold a PhD in structural control along with my bachelor degrees in civil and mechanical engineering. And also, I have been working at Wolfram last 4 years, helping implement and optimize engineering solutions. I guess that is enough about me. Let's get back to today's presentation. In today's presentation, we will first look at the common issues such as roller slippage, tension variability, and breakage. After that, I will introduce the Wolfram Belt Dynamics library and show you how we can use it to address these challenges. Let's start by understanding some common problems faced in roll-to-roll systems. The first one is induced wear and tear. This phenomena occurs due to the excessive friction between the belt and the roller, leading to material degradation over time. As you can see in this image, this can severely damage both the belts and the rollers. Another common problem is roller slippage. This problem can result in machine malfunction, often due to improper tension management. As a result, product quality can suffer. Another problem, overloading or breakage. Excessive torque can overload the system, potentially leading to breakage. It creates such a high tension that it can cause the belt to rip apart or damage the pulleys or rollers. Another one, inconsistent web tensions. The variability in tension can lead to defects in the final product, especially during processes like calendaring. And the notorious problem, vibrations. And these effects can destabilize the system, causing defects or inconsistency in the material. And it can even damage components. Okay, now let's look at how the Wolfram Belt Dynamics library can help address these problems. The first solution the library offers is friction fidelity and monitoring. The library offers precise friction modeling and management, which helps in reducing wear and tear. Another one is the tension monitoring and the capstan dynamic. The library basically enables user to monitor tension and manage capstan effects. Allowing user to detect and prevent slippage. The other one is overload protection and tension control. With this library, you can set safe operational limits in your controllers to prevent breakage due to the excessive loads. Moreover, the library can be combined with the controllers. And the last one, the vibration dynamics. The library offers pre-configured components for high-fidelity models, including vibration-causing components like flexible supports here. Okay then, let's get started with the building some examples using the library and explore its features and see how easily we can model different systems with the library and address the common issues in the roll-to-roll system. Here we see a setup with two rollers, one rewinder, one unwinder. Let's build this using the library. Let's open the Model Center. As you can see, I have already added rewinder and unwinder components. So let's add the missing roller. We simply drag and drop it to the model. The only parameter we need to set is the special parameters like positions. And next, we connect the components using belts. There is no need to set extra parameters. The library automatically takes care of the wrap angles and the contact points. Uh, I guess everything is set up, so let's run the simulations. Yeah, here are the results. Let's first check out the animations. And the animation shows the unwinder releasing the material while the rewinder accumulates it. As we zoom in, we can see the rollers rotate clockwise, just as expected. We can monitor metrics like belt speed, belt tension, and inertia changes over time. For example, the rewinder inertia increases as it accumulates material, while the unwinder inertia decreases. Let's move on to the closed loop belt system. This setup could represent a power transmission or a support bell for paper manufacturing. Let's model this one. In this scenario, we have three rollers with defined positions and diameters, and the belt spans between them, and we have a power source driving the system. Here I want to show one of the key features of the library, which is the belt data component, where we can set parameters like belt density, damping, modulus of elasticity, friction parameters. This makes the setup process much faster since we don't need to configure each belt individually. Now let's run the simulations and analyze the results for this closed loop system. So let's first look at the belt speeds. Here we notice that the belt speed increases initially, but then drops suddenly and continues steadily. This hints us about potential slippage between the belt and roller. To confirm this, we can check the roller speed and see whether it is faster than the belt, indicating slippage at that point. And yes, it is slippage. We can also further analyze this. We can just look at the applied torque versus the capstan torque. In other words, the transfer torque. As the applied torque increases, the capstan torque reaches a limit where the slippage starts. The library ability to analyze torque transfers help us actually pinpoint when and why slippage occurs. Now we have a slippage problem. To address slippage, we can add a nip roll to increase traction between the belts and roller. A nip roll applies pressure to the belt, improving traction and reducing slippage. Let's configure a nip roll to apply 2000 Newton of pressure over here. Here I can also add color scaling to the belts according to their tension in the belt data component. Okay, let's build the updated model. And yes, the simulation has been run. We can check the belt speeds. Here we see that even if slippage occurs initially, the additional pressure allows the system to regain traction. If we compare results to the previous example, the slippage is reduced and the belt speed matches the roller speeds over time. Oh, better not forget the animations. Yes, we can also see customized belt colors in the simulation using color scaling to visualize the belt tension variations throughout the process. Yeah, apart from the nip roll, some systems might have moving tensioners or dancers. There are specific roles for that. To model this, we can assume that, one of the rollers can move back and forth to adjust tension dynamically. The belt library allows us to add support frames that allow the movement of the roller basically. In this case, we will have it move in the x direction, back and forth. Yeah, by running the simulations, we can see how these adjustments affects the belt speed and the tension over time. Okay, let's check the animation first. It shows the roller moving forward, changing the tension in real time. Okay, let's close the animation and let's compare all three systems and slippage. This is the first simulation we see, and here is the second one as well. When we rerun the simulations, we don't see speed difference here, which is because of the roll displacement. Okay, so if we plot the roll displacement, we see that it reached max displacement before the sleep, which was at about 90 seconds for earlier ones. And also, if we check the applied torque versus transfer torque, we see that there is no sudden drop in the transfer torque as well. Yeah, it seems like we solved the slippage issue. And Our next example addresses the vibrations in web handling system. Unwanted vibrations can occur due to flexible supports or maybe bearing selections which might have some flexibility in it. We can model this type of flexibility, these surroundings, using the library by adding flexible supports to the unwinder and rewinder. So when we have the model, we run it. Let's check the simulations, whether we can capture these dynamics. So let's look at the belt tensions. And when we look at it, we see that we have oscillationary behavior, which is because of the vibrations caused by flexible supports. Yeah, by configuring the flexible supports, which represent the additional external damping, maybe in real life, we can just add new bearings with external damping. We can also use the library to model different roll and belt configurations, such as inside wrapped belts, causing the corresponding rolls to rotate in reverse directions, as we see here. And this feature allows for accurate modeling of complex web handling scenarios, like web accumulation or calendaring process. Here we explore an open loop system with half of the roles wrapped inside. Let's simulate it and check the results. Okay, the results are ready. Let's open the animation and see what tensions look like using color scaling to show how the material amount on the unwinder decreases and the rewinder accumulates the material. The rollers at the bottom, when we look at closely, we see that they rotate in the opposite direction of the rollers at the top line, as expected. So I guess it is pretty much of the examples. We have covered a lot of ground today by modeling some of the most common models used in roll-to-roll system like tensioners, web accumulator, open and closed loop belts, from basic setups to advanced configurations. Throughout these examples, we have seen how the Wolfram Belt Dynamics library provides solutions to common problems in roll-to-roll systems. We have also seen key advantages of the library, which include easy model setup, automatic wrap angle calculations, contact point calculations, and integration with other Modelica libraries, such as planar mechanics, rotational mechanics library. Also with customizable friction models and the animation features, we can say that engineers can analyze their system behaviors and optimize performance. So yeah, thank you for your attention. If you have any questions or would like to discuss these models further, I am here to help in Q&A session.
Hello everyone. Hopefully you like the presentation. I am here if you have any questions related to Belt Dynamics library. Um, I can maybe share my screen and continue a bit more about features of it. Yeah, Michael, thank you. Thank you for your nice comment. Yeah, we are just trying to create those libraries so that people are in industry can make use of them. Uh, yeah, that is our ambition. So yeah, we have, okay. Did you participate in the circuit study group? Yeah, I have. I did actually, Michael. Right here we see our belt dynamics library, and over there we have some components which are named like belt and roller. We have winders as well, and in the library when we release it, you will have all the features and all the documentations. What is that about with the corresponding documentations and references? So for instance, the first example talks about the capstan dynamic, what is and such. Another one, for instance, we can have a look like the nip loading, why it is important when it comes to web handling system. I mean, in this library, it is not only for the belt and pulleys. One can easily model the rope and pulley systems and open belt systems. As long as it is roll to roll, uh, this library is capable of modeling those dynamics. What else I can show here? Right, for instance, we have this paper drawing machine. In the example, I try to explain. So here, for instance, for have such kind of calendaring process, I mean, in a scenario, we might have a paper with a certain water content. Let's say it needs to be dried to get a certain amount of moisture content. So what we do in such scenarios, we just create those systems with heated rolls, and depending on the heat transfer we can get out of those rolls, we specify a certain velocity, and that machinery should run at that speed so that we can reach our a estimated or desired water content. And also we need to be really careful about the tension management so that the belt won't get ripped apart. Uh, so for such type of scenarios, we might have like a flexible supports where they cause so much vibrations. We need to model them so that we can take measures like we did over here. We can just include those supports, the flexible supports, and then we can combine these dynamics with the, let's say, the controllers. It can be either a tension control for the belt or maybe the speed control. Those are all can be done with this library. What else I would like to add? Yeah, the nip roll. We have the nip roll as well to just increase the traction between the belt and roller. We can have nip rolls which add nip loading. Also in the library, we have like a pretty unique feature where library restrict us have wrong connections. For instance, if I create this belt again and want to connect that frame to the disk, the library won't allow me to do it because we design these connectors in a way that it will be easy to model. And I mean, if we, while modeling, this type of tricks help us to do really a error-free models. Otherwise, it is really hard to debug and come back and know why this is happening and such. Another nice thing, we are just creating these components and setting this only the special parameters, which are like the dimension and the diameter, nothing more. If we want to increase the fidelity in the model, like adding nip-roll, which can be done, we can just turn the corresponding flag in that component. And also, if we want to include slippage, we can just say, okay, it should be true in this scenario like here. And when it comes to friction models, we have two different models, one being like the column friction, which until we reach that value, the system starts slipping. And the other one is the Strybeck friction, in which we have really well-defined velocity-dependent and viscous dynamics friction model. So it is all up to what is our expectation, what type of fidelity we would like to get from the model. So all those aspects are tried to be included here. If you have any feature, any a fidelity and dynamics you would like this library to include, so please don't hesitate and reach out to me. I will be really happy to answer your questions. So right, I guess that was all related to library and paper making process. Yeah, thank you.